So, our speaker for today is Filippo Mastropietro, and he will talk about Brownian motion over manifolds. Please, Filippo.
Yes. Okay. Hello, everybody. Nice to see you. Two remarks before we start. Today, we will not see two things. We will definitely not see the harmonic measure of a square, since I realize that I can't say anything really relevant about it. But we will say something that it is, in some broad sense, linked to it. So we're still quite fun. Another thing that you will not see today is proofs. Okay, you will see this talk. You have to think about it like some sort of survey of topic that I think are pretty nice, that mix Brownian motions and geometry. So you will see some geometry that some of you might dislike. You will see some analysis that some of you will dislike, and some Brownian motion. I hope that the mixture of the three things will end up being interesting for more or less everybody. Okay, this is our start. What you have seen more or less in the talks of the other guys from my group is this, that if we have a bounded domain omega, then that we will take like this. We learned that if we take a point, that we make Brownian motion starts from there, then we can define two things. First, tau, the first hitting time of the border, okay, the first time our particle that moves of Brownian motion will touch the border. And then we used this information to talk about harmonic measures, so which is in some sense a probability that at this time the manifold, the particle passes through a given point of the border. Okay? And we've seen that this is particularly interesting since it's linked to some more or less standard but very interesting facts analysis. Like you can use it to study problems of this time, let's say, so some sort of Poisson equation for some f. This is on the border, this is on our domain. And we have more or less seen this link. Today we will do a different things. We will study the things from a different perspective. Up until now, we've studied what happens until this time, in some sense. Okay. Today, we're interested in what happens after the first hitting time of the border. So what happens to our Brownian motion when it leaves the given domain that we were considering in the beginning. Okay? In order to give an example, we know that the discrete version of Brownian motion is made by random walks. So consider a lattice in the classical Euclidean space. This is the most classical lattice, just the points whose coordinates are all integer. Okay? We can define random walks as the discrete version, which means given this lattice, we take a particle, again, A, and this has at any time 2 to the d is the dimension, possible direction it can follow. Okay? And they all have the same probability. So at a certain point it will move, but at any time it has the same probability of moving in every direction. The question we want to ask is the following. In this context, we want to know if the particle, after left our domain, if it will ever come back, essentially, to the domain, or if it will, in some sense, escape to infinity. Okay, so in this context, what I ask us is this: will the particle ever return in this discrete version to the point A? Will it return maybe with probability 1, so an infinite amount of time, or only infinitely many times, and then it will get lost? Okay, so these kind of questions are often counterintuitive, and I don't even know really which is the right intuition to have, or what really is intuitive in this context. So I want to try, okay, there's only a few of us here, but I want to try asking you what you believe is true. You believe that the particle will return to the point A an infinite amount of time, or not? So who believes that the particle will come back to the point A, actually? Mattia? No? For you is no? One yes and one no? No. Two no. Okay, two no and one yes. Okay, the answer is quite surprising because what is important in order to understand the answer is that the dimension really gives us the correct answer. Okay, what happens actually? It happens that if the dimension of our space is 2, then the particle actually do pass from A an infinite amount of time. Okay? Infinitely many times. And for all the bigger dimension, so 3 or bigger, the particle will hit A at most finitely many times, and then in some sense it will escape to infinity. At most, finitely many times. Okay, this is a bit surprising actually. What's happening is this. Since every direction has the same probability, one expects that in some sense the particle moves up, and then at a later moment, there's the same probability for every direction, so that will be another moment in which it goes down. And so in this sense, it should compensate on it, and the particle will be on average close to A. That's what one expects to be true often. The surprising answer is that in dimension 2, this actually happens, and the particle always comes back. In bigger dimension, and this is quite surprising, this does not happen. We can start thinking of the reason. In some sense, when there are too many degrees of freedom, the particle manages somehow, we understand it better, you know, to get lost in the road and to never come back. While in 2 dimensions, this does not happen. This is quite a peculiar thing that happens. And it happens also in the continuous version. So we will give these 2 definitions. Definition, we say that Brownian motion is recurrent in the first situation. Okay? Brownian motion, Vn is recurrent if for every bounded domain the particle enters and goes outside infinitely many times. The particle hits the border. Infinitely many times. Otherwise, we say the particle is transient. Okay, so our first example, okay, this result also falls in the continuous setting. So our first result, which is a result of Olia, where is it? Theorem. It's a pretty old result. Okay. R2 is recurrent. And Rd for any bigger d is transient. Okay, so in R3 or bigger, the particle that moves of Brownian motion somehow get lost. In 2 dimensions, this does not happen. Now, an interesting thing, but we will not say much about this, is that this is linked to some analytic fact that more or less everybody should know. Somebody probably forgot it. But it's this fact. We will not say much about this, but those of you who are well fond of analysis maybe will appreciate. The difference is linked with this difference between the dimension 2 and the bigger dimension. In dimension 2, the green kernel, maybe we'll define it again, we have more or less already seen it in Mattia's seminar, but I'll define it again. The green kernel has this form, up to constants, okay? A constant times the logarithm of the distance of x and y. While for all bigger time, it has a very different shape. It is a constant times this thing here. So the green kernel, what is it? It's the things that solves for any y this thing, and it is the Kronecker, the Dirac distribution centered at y on the, come si dice? Dammi una mano Mattia. It solves this on RT minus y, and when it tends to y, it behaves like the Dirac delta, okay? This is a distributional solution. Okay? The crucial fact is that we have already seen this green kernel, and we know it is linked to Brownian motion. The fact that it is so much different in dimension 2 and bigger is somehow the key for this different behavior. And the reason in which sense they are different, for example, this function changes sign, and this one not. And this is a really, really important fact we will not investigate on each more. Okay? So, now let's pause for a bit the analytic part, and let's move to geometry. What we're going to do from now on is this, okay? We see the first two examples. We want to study the geometry of Brownian motion. What does it mean? It means that from the properties that the Brownian motions has in a certain domain, we want to obtain information on the domain itself. Okay? So this is the first point, okay, the starting point. Okay? If someone lives in some sense inside a plane, he will see different behaviors than if he lives in a bigger dimensional space. So in some sense here there's the first glimpse of how the properties of Brownian motions affect geometry. So what we're going to do is set Brownian motion on a manifold and see what these sort of properties and other properties that we'll see will tell us about the manifold itself. Okay? So let's give a short recap of what a Riemannian manifold is in a very elementary way. At a very elementary level, again, a Riemannian manifold is just a topological manifold with a function with this form, which is a function which takes tangent vectors, okay, in this way, such that it is R bilinear, and I assume that you more or less already know what this means. It is smooth, okay, and it is definite positive, which means we arrive with that the norm of any vector is non-negative, and it is 0 if and only if the vector is 0. This is a Riemannian manifold, which is our mathematical model for describing objects with a notion of curvature. Anyway, this is, of course, an ugly definition of what a geometric object is, because it's very intrinsic. So, in our mind, a manifold is just something that lives in a three-dimensional space because it's the only one that we can actually picture. So let's see how this definition relates something a bit more intuitive. The content of this theorem is Nash theorem, and in this form it was proved in 1956. The point is this: with this abstract definition of a smooth Riemannian manifold, because everything is smooth at this point, there always exists an isometric embedding. We'll see what this means. M with its metric inside an Euclidean space of some dimension. Okay, isometric embedding just means that we can see this like some sort of smooth subset of Rn with its notion of metric, which is just the one that inherits from the Euclidean space.
That's also a metric space, right?
That's also metric space, yes. If you want to know how you compute the distances with this abstract notion of metric.
Yeah, I'm just saying like that manifolds are also metric spaces.
Yeah, because okay, you don't immediately notice from this definition of G, but it's very easy to define a metric in the old sense, okay, in the sense of a distance. Because with this definition, you can compute the length of curves. Why? You have a curve on your manifold, and its length is just the integral of the norm of its tangent vectors.
It's a normal space.
It's clear. This, you obtain the length of curve. The distance between 2 points is just the infimum of this length between all curves. You want me to write it down? Clear? So yeah, this is also metric space. And the metric it has when it lives inside here, since it is an isometric embedding, is just the Euclidean one, actually. Okay, computed in this way, again, but distances are the distances that you know, more or less. Okay? The important thing that we have to keep in mind for later moments is that this dimension can be much bigger than this, actually, okay? So the point is, we are used to thinking just of things like surfaces in three-dimensional space. Okay, our intuition is correct. Manifolds actually are these things, but sometimes they need a much bigger space to be embedded. Okay, so there are, for example, surfaces, so two-dimensional things, that can't be embedded to R3, but maybe to R4, yes. Okay, this is important for what we arrive later. So there are manifolds, two-dimensional manifold that can't be embedded, that can be embedded. In R4, but not R3. So sometimes manifold, in order to be represented, need a bigger space. 3 dimensions are not enough to represent it. This will be important.
Is there any bounds on?
Yeah, there is. I didn't write it down, I don't remember it by heart. But there is a bound of the maximum dimension of n, knowing its dimension. Don't remember exactly, likely, but yeah, of course, that's a good question. Okay, so we are right. So this is in some sense also the reason why we need an abstract definition like that. Okay, our intuition behaves better if things are embedded, of course. But sometimes, again, even just in a 2-dimensional space, we need a 4-dimensional space, which is something we can't visualize. And sometimes we will see right now that that definition is much better for defining elementary objects that in this sense are really, really hard to define. Okay, so we need that. A curious thing, don't know if it's interesting, is that look at the date. This Nash theorem was proven like 70 years ago, more or less. Okay, Riemannian manifold are defined after Riemann, who died in this date. Okay, so for more or less a century, we have not been sure that this definition really matches our intuition. It is something really peculiar to me. But yeah, manifolds are just these smooth things inside here with this notion of distance. But for 100 centuries and more, the definition we use of manifold is more or less the one for Riemann. So for 100 centuries, more or less, we didn't even know if actually those things matches our intuition or not. It's pretty peculiar, if you ask me. So now let's see quite quickly two very, very quick examples of Riemannian manifold and why it is important to define in this abstract way, and then we'll come back to our Brownian motion, of course. What?
Nash from the Nash theory.
Yeah, it's the same Nash. It's the same Nash, yeah, the one of the movie also. Yeah, he did research on really a billion different topics. That's quite surprising. Okay, so two basic example of what Riemannian manifolds are. Okay, the most stupid example, of course, is Euclidean space with its just in 2 dimensions for now, which is usual metric. Okay, the usual Euclidean metric, you know it. Of course, we have our plane, and the axes are orthogonal, and it's one you always know how to compute everything. Okay. In our abstract notation, we write it this way. We will not really need it for much, but I will still write. So of course, some of you are not used to tensor products, but this is just an odd way to intend the classical metric. Okay? And in a more compact way, we write it like this. It's not really important. We just need it for the next step. Because the next example is is very, very important, but a bit less intuitive. Okay, so take in the Euclidean space, in the Euclidean b-dimensional space, an open disk. Okay, no border here. What we're going to define right now is a model of the hyperbolic space, which is very important. Now we will take on this set this metric here. This is the letter we use for the hyperbolic space, which is 4 times. It is just the Euclidean metric, but it is multiplied by a function. We try to figure out what's happening right now. So we take a very simple object, which usually would have a metric like this, and we change a bit the metric. So the numerator is just that metric multiplied by 4. The denominator does this function that multiplies everything and rescale the metric. That's what it's basically doing. What's happening, more or less, just to give some sort of intuition of what a mess like that would mean, is this. We have a unitary disk. Okay. This term here is rescaling our notion of distance. So what actually happens is that when we are really close to the origin, this thing is 1 and the metric is more or less Euclidean 1. But when we reach the border, this term is going to infinity. Okay, this is at 0, so all this is going to infinity, which just means that lengths are stretched. Okay, so in some sense, this piece here is incredibly long, and actually this curve in this metric, the one who reaches the border, has infinite length, actually, in this metric. Okay, that's the only thing that I want you to keep in mind on this space. Okay, so that's an example that we need, but the hard geometry is over. Okay, that's all we're going to. Why this is so important, and what's the relation to Brownian motion? It's very important because what do we do in geometry all the time? The most important results are classification results. Okay, so the things that we really hope for is that these spaces are some sort of models for all the possible spaces, at least in dimension 2. Okay, and the really surprising results are the one of this type, and the one we try to cook up all the time. So where is what they found at the beginning of the 20th century is this theorem that is really probably the most important in Riemannian geometry. Okay, so I need a better chalk right now. This is called the uniformization theorem. It's from 1907, and it's due more or less, okay, a lot of different effort of different mathematicians. These are some most important contributions are by Poincaré, which is pretty famous, Klein, which is pretty famous, and Visco-Begaise, which is less famous, actually. It states the following. A simply connected, I will see again what simply connected is for those who don't remember, but it's a pretty simple property. Riemannian surface, which mean again, it just at least two-dimensional, is, this is very important, conformally equivalent, and maybe some of you will start to see the link to Brownian motion, to one of those of the space I'm going to tell you about right now. These spaces are easy, actually. What is it? Okay. The sphere, of course, the sphere is a Riemannian manifold. It lives in the three-dimensional space, okay, and it has a metric that inherits from there. three-dimensional space, the Euclidean space with its classical distance, and the hyperbolic space. If, okay, this is not very important. This is it's. So what is this theorem saying, actually? It's saying that these are really the model for more or less all the geometry that happens in 2 dimensions. This is an amazing result since it's just 3 simple spaces. So a simply connected manifold, for those who don't remember, is just a manifold in which you draw a loop in it and you have enough space to stretch it until it becomes a point. For example, a cylinder doesn't work. Okay, you can stretch a circle inside a cylinder. But the sphere works, you can stretch it. Okay? Conformal equivalent is something that you have already seen, and so maybe you're starting to get used. Conformal transformations are the one who preserves angles. And in 2 dimensions, I will write it anyway. Come on, I write it again. You've already seen it in Mattia's talk and also in Francesco's talk, and of course, Giovanni's talk. And so conformal transformations, again, basically are just the one that preserves angles. They preserve angles, but not necessarily distances. And in 2 dimensions, they are the same as holomorphic map, whose derivatives doesn't map vanish. Okay. And we have already seen they're very linked to Brownian motion. So the point is this: if you forget about distances and only decide that you care about angles, all the manifold looks the same. That's what's out. Or the simply connected one really looks the same. There are just 3 possibilities: sphere, Euclidean space, hyperbolic space. Okay, and so this is, of course, an amazing result. Now, I will not really delve into what curvature is, but I will talk about just with an intuitive idea what curvature is. So a sphere is said to be a space of positive curvature, and I will talk about a minute later. This is very important. This is the flat space, okay? There's no curvature in a plane, of course. So this is 0 curvature, flat. And this one is the fundamental space of negative curvature. Constant curvature. When I say positive, I say its curvature is 1. Okay? Its curvature is 0. Its curvature is -1. And so this is the fundamental fact. Every space can be transformed. Okay, we have this notion of curvature. We'll talk about it in a minute, but it's the essential one in Riemannian geometry. But every space can be transformed if you just decide that you care about angles but not length to this free space here. Okay? The one with the simplest positive curvature ever. That's an amazing geometric result. Again, there's a billion of properties inside this result, but I won't delve too much into it. Okay, starting back. Okay, in a minute we will come back to Brownian motion. Just keep in mind what we said here. All the spaces in dimension 2 can be transformed in one of these 3, and this definition will come back, recurrent and transient. Okay, in a minute. Before doing that, just a slight intuition of what we mean by positive and negative curvature in a minute. The actual definition of curvature in every dimension will be a mess, and I won't give it to you. Okay, but a point on a manifold of positive curvature is just something that really resembles how the sphere curves. Okay, so you really have a sphere and a point here. What's happening in some sense, all the curves in a sphere are going in from this point. Okay, there's some sort of convexity at this point. Okay, it's not clear the drawing. Okay, so this is a positive curvature. So positive points of positive curvature are locally very similar to a spheres, and it just means this. Take it as a tautology, the one I wrote there. Okay, negative curvature is a bit more complicated. Imagine a sepal. Okay, so something that in this direction goes up in some sense, and in this direction goes down. This change of behavior is what makes negative curvature. So think of saddle points are the model for point of negative curvature. Okay? The point is this. Hyperbolic spaces I had to define it in that strange way because there's no real way of embedding it in R3, as I said. It needs more dimension. And that's typical of negative curvature. When you have positive curvature, things tend to become more or less like spheres, and we can embed it in a three-dimensional space, of course. Of course, not all the time. But when you have enough negative curvature in some sense, the space will not be embeddable no more in three-dimensional spaces. So it's a space that becomes more different to picture and more interesting, because what we'll do now is to learn how Brownian motion helps us in some sense to detect the behavior of spaces like this. Okay? So we have our uniformization theorem, which tells that all the spaces can be transformed like this. Okay? The point is this. There's this problem, classical problem. Let me just take, where did I wrote it? Okay. Here, which is called the type problem. What does it mean? It means that if I give you a manifold, in this case a surface, I want you to tell me in which of these three classes it belongs to. Okay? But we only know that up to transformation they become one of these, so in principle it's very difficult to understand what will happen, because conformal transformation can be pretty hard, of course. So given a manifold, how you identify in which class it actually belongs. So it can be conformally transformed in something like this. That's a difficult problem, but it was addressed, and one possible solution, so a necessary and sufficient condition for understanding which is given by Brownian motion. That's the surprising fact. Okay? So the sphere is not interesting because the sphere is compact. So it's very simple to understand. Okay, so it's different from the two others. So what we're interested in is the ones that are not compact, actually. So how do I distinguish, more or less, a manifold which can be transformed in Euclidean spaces from how that can be transformed to hyperbolic spaces? Okay? The surprising property is that the answer is given by Brownian motion. And this is a classical result. This was proven by, let's say, this is a theorem. This was proven by Alfors in 1945. Okay? And it's this exactly. We will call, okay, parabolic manifolds, the one who can be transformed in something like this. Okay, this one we will not really call it hyperbolic for some reason, just non-parabolic, for reason that I won't really explain, because there are many notions of hyperbolicity, so we don't want to get confused. So the manifolds that become this after conformal transformation are parabolic. In this one we will say it's an ugly term, but we'll say non-parabolic just. That's a great property. We know that R2 is recurrent in the sense that Brownian motion has this property. We know that conformal transformation preserves Brownian motion. We said Francesco Monzani told it, everybody told it in the seminar. So the important fact is that conformal transformation are well behaved with respect to Brownian motion. So every time I transform R2, I remain recurrent. Brownian motion in there is always like this. And so the theorem is a surface. Let's say simply connected. Okay, it's not really a restriction, but it's simply connected. Non-compact. Okay, a non-compact surface and simply connected is parabolic if and only if Brownian motion is recurrent. This is a surprising link. Okay, this is more or less a really old result. Okay, 1935. And so it's more or less established, but it's something that is not really well known. So Brownian motion is the key to distinguish these spaces from these, because then what happens, since I said if and only if, there it will happen that a non-parabolic manifold, so the one that are like hyperbolic space, are exactly the transient one. Okay? Okay, one should add this definition, which is the definition of completeness, in order to this really makes sense. You can think of completeness as for usual metric space, okay? So Cauchy sequences always converge. We have a distance, so you can think of that notion of completeness. There are also others, but that one is perfectly fine. Okay? So we learned that all non-parabolic manifolds, okay, are transient. So Brownian motion always escapes at infinity. And this is our key property. Now, Brownian motion relates to geometry, because it tells us if there is some negative curvature, in the sense that I can transform it to something that has always negative curvature, then this Brownian motion will tend to escape at infinity. Otherwise, it will somehow always come back where it started. Okay? That's the really surprising point. And these are, I hope, the last 10 minutes. I want to give a bit of intuition of why it happens and what's happening in here. Okay? The intuition that will help us also describing some other pathological phenomenon that don't happen in Euclidean space. So the important thing is there are two-dimensional things that are transient. They're just hyperbolic. Otherwise, you need a bigger space. A bigger dimension also is transient. But even staying in 2, we have hyperbolic space. I want to give a little intuition of why this happens. Okay, and then we're almost over. Imagine, okay, a flat manifold. Okay, a plane is flat. Okay, there's no curvature in that. What happens is the following. We take a point and take a ball. Okay, it's a horrible picture, I'm sorry. but you understand what's happening, okay? Okay, a ball in free space, then the intersection is just the usual two-dimensional disk, okay? And it has the volume of the two-dimensional disk, okay? But what happens in the presence of curvature, if I do these same things, let's take a manifold, which does something like this, okay? Again, a really ugly. Is a really ugly picture, but okay, we'll save that. If I do the same things and take a ball here, what will happen, come on, that's disgusting, is that if I really twist the space in here, there will be more and more volume inside this space, okay? I will write it again because it's really terrible picture, that one. Okay. Just think of curves, okay? A straight curve, I take a disk, and it's just a segment. But if I really twist it a lot, if I make it curve a lot, you take a ball, and there's much and much more space inside, okay? So recurrence and transient are about having enough space that the particle actually gets lost, okay? I can do it by enlarging the dimension, but if I add curvature, I can also obtain the same result, okay? In this sense, in a little ball, there is enough space, if I add curvature, that the particle can actually manage to get lost. And that's the intuition behind it, the curvature of balls, in particular their behavior while they get much and much bigger. Okay? But I need so much space that my manifold will not be representable anymore in a three-dimensional space. That's more or less the idea. I need so much space in order for the particle to get lost that I obtain manifolds of this type here that tend to not be able to be represented in the classical space. But this is the key. Okay, the key intuition is this, the growth, in some sense, of the balls in this space. They tend to have more volume. A ball of a fixed radium in the metric of a curved manifold tend to have much more volume if I have enough negative curvature. And that's the key. That's what happened, and that's the key to understanding the next thing, and then I'm done, which is a really nice behavior that doesn't happen in Euclidean space, okay? This happens in Euclidean space, I just need enough dimension. The next one is a pretty special one, which is this. Our curvature, in some sense, negative curvature, helps the particle getting lost. And that's very interesting. In some sense, it's like it drifts the particle towards infinity. There's some sort of acceleration of a particle that moves through Brownian motion when there's curvature, and so it goes faster to infinity, okay, and never come back. The surprising point, if I take more curvature than this also, enough curvature, it can happen a really pathological phenomenon, which is called the explosion of Brownian motion. That means that the particle, the start of Brownian motion, reaches infinity in a finite amount of time. So the actual definition, where is it? Which is a really surprising fact. Stated more properly, it says like this. Okay. Explosion of Brownian motion means the following. The total probability of finding the particle inside my manifold is actually less than 1 at a given time. particle inside the manifold is less than 1 for time big enough. Which means there is a positive probability that the particle actually escape from a manifold. The incredible thing is that this also happened for complete manifold. What do I mean? I mean that of course my manifold is incomplete in the sense that it's just, let's say again, a bounded domain. And I call this my manifold, the Euclidean metric. Of course, this is incomplete in the sense that I have a Cauchy sequence that reaches the border and then disappears because it goes outside. So of course, this thing has an explosion behavior. But if you put enough curvature in this situation, also for complete manifold, which have no holes, the particle can just fall down at a certain point and disappear. A particle which moves over Brownian motion will actually do it because in some sense it will just disappear at infinity. And so the Brownian motion has a short time living. After some time, the particle in some sense dies. And this is a really pathological behavior that can't happen to Euclidean spaces, of course. Okay, you need to impose a lot of curvature to start seeing this strange phenomenon happening. And that's more or less what I wanted to say for today. Okay, there are some points about how we can link this to analysis on manifold, but I think it's okay if we just leave it here. Okay, and again, okay, I will just state this. The fundamental property is the same again. The notion we really need for understanding if a manifold has or not this behavior is the volume. Okay? In any manifold, I can describe a ball of radius r centered at fixed point 3. Okay? Because it's a metric space. Okay? The fact is that its volume can be very different from the usual Euclidean case, because when a manifold chord aloft there can be more volume inside. Okay? And again, this is the fundamental property. I present you these two theorems and then I'm done. So on any, okay, now I'll go here. On a manifold M, Brownian motion is recurrent. If this condition is satisfied. So this is the radius in the notion of distance. The integral of the radius over the volume of balls reaches this quantity. So this is telling us that there is enough space. If one computes, for example, a ball of this type, whose volume is something like c to the r squared, satisfy that condition. If it's the Euclidean space, of course, we have balls of this type. And so we recover our case. But ball which moves faster, don't do it. And so in higher dimension, this doesn't happen. And in fact, it's not the case. But also explosion as a characterization in the term of hypothesis. And I give it to you. Now, again, theorem, Bm is not exploding for any time if this condition satisfies integral of R over the logarithm of the same thing, the volume of, okay, this is getting ugly again, is infinite. Okay, if this condition is satisfied, there's no explosion of Brownian motion. This happens if, for example, we have volumes that are really big. So we need something like e to the r, okay, in order to have condition, or e to the r square in order to have the condition of this, okay? manifold who curve less, and this is really a lot, okay? Don't see this strange phenomenon of explosion. But if I can manage that, and it is possible to achieve, okay, you have your condition. And that's, okay, that's more or less all I wanted to say. I think it's enough, otherwise it's getting a bit annoying.
Okay, thank you, Filippo. Is there any question? That does not seem to be the case, so we thank Filippo again. And we resume tomorrow for our last talk. Thank you.